Swayam Prabha. Digital India. Educated India.
So, good morning. Today we will start the lecture number 2 on module number 1. So, initially we have introduction module. In that we are going to talk about some of the introduction to the building physics. We will start the physics portion today. The thermal properties of matter that I will going to discuss in the consecutive 2 lectures. So, in this particular lecture number 2, I am going to cover the heat transfer mechanism, conductivity and the transmission and the transmittance of the heat, and also the periodic heat flow. So, if you see the flow pattern or the heat transfer in building, it mainly occurs into the 3 ways. The first one is called the conduction, which is a kind of the flow of heat from one point to other if there is a kind of a temperature gradient exists. What is a temperature gradient? There should be a differential temperature exist in the from one layer to the other layer, otherwise heat will not going to transfer. Now, in this particular case, in the conduction case, the heat will be transferred through the solid media, and it will be actually transferred from one layers of particle to the other layer of particle, and then the other third layer of particle, like that. So, by virtue of this particular movement you require a solid media, and that is called the conduction. So, all the material exist in this earth, and some of them are we are using for the buildings, are actually exhibit the conduction of the heat. The second process is called the convection of the heat, which actually talks about the transfer of the heat or the movement from one point to other by some kind of a temperature gradient, but this will be through the fluid molecules. Fluid molecules in that include 2 type of fluid. One is it is a gaseous media, that means mostly the air in our case, or sometimes also maybe with the water or any kind of the liquid media. So, any kind of the heat exchange through the window because of the natural ventilation, or any kind of heat exchange process inside the building because of the air conditioning and all is actually, or maybe you just run a fan, ceiling fan, or maybe a stand fan, it is a kind of a convection of the heat from one place to other because of the change of air from one point to other and carrying out that heat. The third one is called the radiation. Radiation is a process where you do not need any kind of a media. Basically, it is a propagation of the heat through the electromagnetic wave. Actually, heat is a electromagnetic wave, and it has a kind of a frequency or the wavelength band. So, suppose from the sun the heat comes to the earth, and there is a lot of amount of space available where there is no air, nothing is there, but still we get the heat because of this electromagnetic radiation is a radiant energy that comes from the sun to the earth. So, any the hot object actually placed inside a room, maybe it is a very hot wall, or maybe very hot window, or maybe some kind of the instrument, maybe a heater. So, from there the heat actually may transfer from one point to other through the radiation. And if suppose if I imagine that particular room does not have any air, still that particular the energy will propagate from one point to other. So, now let us see. So, these are the one of the basically a conceptual picture that from the all the envelope surfaces, which is actually the solid surfaces, the conduction will take place, the radiation will take place, and then from the solar radiation it comes through the window or maybe any kind of glazing or any kind of the skylight. From there the radiation can come in. The convection can come through, maybe through window or maybe some kind of the openings in the envelope. So, from there the convection, and then it can get lot of the heat gain will be there in the particular building inside. So, we will now talk about some thermal conductivity because this is one of the very important thing that we should take into account when we going to model any kind of building, and when we go for some kind of assessment of some kind of the maybe we can see the initial the fundamentals physics of this thermal conduction. It's actually mathematically follow a law called Fourier law. Sorry, this law stated that the heat flux, that is I have denoted as Q suffix x, is minus k into dt dx. Actually, if you see, this is the Qx is proportional to this dt dx. This dt dx is the thermal gradient, that there is a kind of a external temperature and internal temperature, or the two temperature both the side of a particular object exist, and there is a differential temperature exist. So, this is there is a differential temperature exist, and this the x, the change of the length is this one, this length is the L. So, it is depend upon the how thick it is or how thin it is, and also the how much is the differential level of the temperature difference between the two surfaces. It is actually going to say that this kind of law is also exist in the electricity, then where there is a voltage drop, voltage exists, there is a voltage difference exists, there should be a pass of current. If there is a height difference exists, there will be a pass of the flow of water is exist in through a pipe. So, those are the some of the cases which can actually replicate with the thermal conductivity Fourier law equation. And finally, it has to have some constant called the K, or it is called the K value, thermal conductivity of the material, which is a unique property of the material, which denotes in watt per meter square degree centigrade. Something like the density is a very unique property, something like the specific heat is a very unique property, something like the expansion coefficient, that alpha value of a material is a unique property. This K is also a very unique property of a material. So, here as I told you, this dt dx can be replaced as T2 minus T1, that is the differential temperature. And if this is 0, that means there is no differential temperature. So, that means both are equal, there will be no heat passes through from one end to the other, and that divided by the L, the thickness of the object, and Qx will be defined as that as K into the T1 minus T2 into L. Now, here if I multiply this Qx into A, because the Qx is what is the heat flux, it is the watt per meter square. As we all know now, that in the first lecture we have discussed that the watt is the rate of energy passing from one point to other, that is joule per second. So, per meter square area of the envelope or maybe any object, how much heat is passing through per second, that is your heat flux, that is your Q. Now, if I multiply that Qx by A, that is the area of the total area, instead of the 1 meter square area, whole area, if I know the what is the width of that object, what is the height of the object or length or height. So, I know that particular sum of the area, that particular area, how much total heat is actually entering by the conduction method, and this Qx, the capital Qx will be in what, because I have already multiplied with the meter square. Okay. So, this if I multiply with Kx, then it will be a watt. So, this is the first fundamental that we should understand. We have developed a material property or understand a material property like K value, which is also called K value. This thermal conductivity will come into that. So, what I am written over here is that the conduction of heat through a body can seen in the spreading of the molecular movement from one point to other, and this particular the how fast that particular heat can be conducted from one point to other, how quickly or how slowly depend upon that particular K value. Suppose you can keep both the T1 and T2 in same temperature difference, maybe 10 degree or 20 degree, whatever it may be, and you can keep maybe 1 centimeter thick or some unit amount of thickness of the material. All the material will exhibit different type of heat conduction, Qx will be different. So, some of the material will have very high value, some of the material may have a high value like almost like 400 watt per meter square degree centigrade. So, it will actually allow 400 watt, 400 joule per second per meter thickness, and if there is a drop of 1 degree centigrade. But some of the material will be very we can say that are the insulative material, they are having very low, almost 0.03 watt per meter of thickness and per degree C of the temperature difference. So, those are the insulative material like wool or maybe some extended polyester or those kind of a material, whereas the metals show almost like 400 or more than 400 sometimes. So, that is the very unique value, that the thermal conductivity, we call that value as a K value. So, please remember this K value has a unit of watt per meter per degree centigrade. So, per unit of thickness, if there is a 1 degree temperature difference, how much watt, how much joule per second the energy is transmitted, instead of transmitted I must say it is how much is conducted from one point to the other. So, I have listed down some of the K values of some material. Plaster is 0.5, whereas you see if it is granite it is 2.3, you see this is 2.3, brick is 0.7, whereas if you see the air is 0.05, it is very insulative kind of material. EPS, extended polyester, something like a thermocol, a hard kind of a thermocol, is almost 0.035 like that. And also I have listed down the density values, also have listed down the specific heat values, those will actually required afterwards. So, these are the some of the recommended values of the material which usually we use for in the building. Concrete has 1.33, the glass is having 1.1 watt per meter square degree C. So, now we will do example. Suppose a wall is made of 2 such material and the K values are mentioned. The first layer, the right hand side layer is of 200 mm thick, and second one is 100 mm thick, and the K values are 0.5 and 1.5, and the one side the temperature is the 40 degree centigrade and another side is 20 degree centigrade. So, there is a there is a temperature gradient exists. So, my question is how much will be the temperature at this particular junction and how much will be the heat flux. If I want to solve this, so I know the heat flux will be the same, because heat cannot be in a particular steady state situation, heat will be whatever heat will come in one side, that will be actually go to the other side, right. In case of the steady state situation, initially it will not show like that, because some of the heat will be absorbed by the layers and there will be some kind of the changes. So, by virtue of the continuity equation, so this if I say the Q1 is the gradient from the first layer. So, I have written down that T1 minus theta by B1. So, B1 I have replaced this L. If you remember this, the equation is Q is equal to this K and this is T1 minus T2 by L. So, here I have the first layer, the right hand side layer, the one side it is T1 and another side in the junction it is theta and the thickness is B1, and the second layer, the left side layer, it is your theta 2 T2 and there is a B2, the thickness is different thickness. So, now I replace all the values and I know the Q1 must be equal to Q2 because of the continuity, and I can solve for the theta. Everything I know B1 is 200 mm, B2 is 100 mm, but I have to put the B1 B2 values in meter, not in other unit, and K1 K2 is also given to me 0.5 and 1.5. T1 I know, T2 also I know 40 degree and 20 degree. So, everything is there, only theta is not there. So, I can solve for it and I can find out that theta is almost about 22.85 degree, and just replace the value of theta in some of the one of the equation. I can say that the heat flux is almost about 42.8 watt per meter square. So, like now like that, if I add up, because you know the in reality there is in building envelope or maybe anywhere in the roof also, maybe in the floors also, we have 2-3 different type of material. We may have a brick layer, we must have some kind of a the plaster minimum, or maybe we have a cavity wall, or in the roof we may have a the RCC roof, and over that we may have some kind of protective, that waterproofing layer. So, there are 2-3 layers of material. So, through that, and they have different K values. So, it will should exhibit in this way. So, this is the then what happened is that for that particular scenario, when there is a different type of material, suppose this is the 2 layers of brick and in between there is a the insulative layer. So, something like this is your the hollow blocks and there is a insulative layer. So, each layer will have its own K value, each layer will have its own the thicknesses, differential thicknesses. So, based on that, a composite conductivity or composite value will be coming with that particular combination, which is called transmittance value, which is further very important in the sense the K value is very basic, but I want to use this transmittance value, or it is very popularly called as U value. So, that that will be readily available with me, and I will actually use that particular value for any kind of the heat load calculation, for cooling load calculations or so. So, otherwise I have to every time I have to do the layer by layer calculation with the K value. So, in that the composite U value is suppose how to what is the formula or what is the equations or so. So, you see this is one of the cross section of a wall I have shown, and it has two materials. Suppose there is a red color material and there is another color material. So, there are 2 materials have 2 different K values, maybe it is of your brick, it is of your plaster, or maybe you have a air gap. So, those are there and they are having different thicknesses B1, B2 like their different thicknesses, and you see this particular the wall will have some surface resistivity, and the surface resistivity which will try to protect the heat to conduct, and that depends upon lot of things, that depends upon the color of the particular wall, that particular the texture of the wall, and what is there is a film of air will be there in the both the airs the wall side. So, based on that there is a resistance in the outside and the resistance in the inside. So, based on this RSO, that is I am calling that as a resistance surface outside, resistance of the surface inside, and if I include these actual values of the material K and the thicknesses, then the U value can be calculated based on this particular formula. So, it is 1 upon the inverse of K and multiplied by the B. So, if this 1 upon K is 1 upon K is called the resistivity. So, I multiply with the B into K, that B is the thickness, and this is for the first layer, second layer like that. So, B2 by K2 like that, and I add this is the resistivity. So, I can directly add the RSO and plus the RSI. So, I got the whole resistivity of the whole layer. So, it is the kind of the equivalent resistivity of the layer, and if I am reciprocal I am getting the reciprocal of that to get that particular transmittance value. So, this value is called the this reciprocal value is called the RA to A. A to A means air to air, that means outdoor air to the indoor air is the this value, but this RSO and the RSI is very small. So, sometimes we ignore. So, if we want to ignore it, then I can also write this u value is something like that 1 upon this 1 upon r, sorry not r, this will be b 1 by k 1 plus b 2 by k 2, like that. I can stop that to this without taking the add to add, but because this will be very negligible, but sometimes we can add it. So, in that we can, and this particular value is called the u value, and the transmittance value, that it has a unit of watt per meter square degree C. Please remember, the k value has a unit of watt per meter per degree C. Now, it is watt per meter square per degree C, that means per square meter how much watt. So, just if I multiply with the amount of area, I can directly get, and if I multiply with the how much is the temperature different, I can directly get the heat flux or the total heat that will flow from one point to the other. So, let us calculate. Suppose I have a typical the brick wall 115 mm thick brick, which is having a k value of 0.7. This is the thick 20 mm thick plaster of k value of 0.5, 12 mm of plaster another side, and that is 0.5 again. So, as per my, and those things are the RSO and the RSI values are the mentioned over here, and this is the a kind of a constant value. It also changes, but we can say this is a constant for our calculation. And then I am going to use this equation. This has 3 layers. So, there will be B 1 by K 1, which is your first one. If you see, this is your RSO. So, this is your this, and this is the last one is the 0.13 is the RSI, which I have mentioned here and here, and this 3 is the middle 3. So, first one, this is your 20 mm thick, and this is 0.05 for the plaster. This is your 115 mm thick, I have to transfer it to meter, and this is your brick, and this is your again 12 mm plaster, and this is your this k value of the plaster. So, by doing that, we can finally find out that the u value is 2.51. So, we will add up, and then again we make this kind of the reverse the reciprocal of that, and we can find out the u value is 2.51. So, we may say that a particular brick work having 115 mm thick and plaster both the side 20 and 12 will have a u value of 2.5 watt per meter square degree C. So, that means if there is a 1 degree temperature difference, and then if there is a the 1 meter square of the area of the, if I see, it will transmit almost about 2.51 watt. If there is a 2 degree difference, then it will be of almost 5 watt, double of that. If there is a 2 meter square and 1 degree difference, again it is 5. So, like that we can just multiply with the area and the temperature difference between the two sides, we can find out this. So, I have calculated for 5 inch brick wall, which just now I have calculated as 2.5 or something like that. I have also calculated for the 10 inch brick wall, just changing the value, this value, the millimeter value as point instead of the 115 to 250. So, the u value is reducing. U value reducing means it is less, I mean it is tough to penetrate. The transmissions is very low with compared to the 5 inch wall or so. So, that will be required for much, that will give you much more protection from the heat also. So, I have a Excel sheet, I will show you, and so I have given 3 layers, and that particular table I have mentioned over here. So, in this Excel sheet we can calculate the u value of the composite wall. Maximum 3 different layer can be taken into that, and this corresponding k value can become in the yellow mark. So, suppose if I go with some kind of instead of this is the 0.35, suppose I am going with some kind of plaster. In one side plaster is having 0.5 over here, and 250 wall, and there is a 25 mm thick 25 mm thick, this is your this EPS, that is your this thing. So, the U value is 0.9. Okay, see, if I suppose instead of the 1 inch, that is 25, instead of that if I put 50 mm this thing, the EPS, that is the insulative things, it is again going reduced to 0.55. So, I will share it this with you, you can actually go through this. So, there are different U values. So, smaller U values are very good, right, because it will be very good in the sense for the protection of the heat protection or so. So, you see the brick cavity with 5 inch brick cavity and the 3 inch air cavity with the, so 3 inch air cavity with 2 layers of work, brick work of 5 inch and 10 inch, it is almost 0.27, whereas you see if it is only 10 inch brick work, it is 1.7 almost, and the maximum one may be the 6 mm glass, which is 5.7. So, which is your U value. So, U value is definitely will better will be the heat less U value, because that will be conducting less amount of heat and it will require, I mean that will be actually give us less amount of heat load or the cooling load. So, as I told you, so we can find out this Q by just multiplying the area of the wall or the envelope with the corresponding U value, suppose it is brick work or your cavity wall, whatever, and the delta T. Delta T is your temperature difference, that means the temperature difference between the outdoor and the indoor. So, if you take the average outdoor temperature as 35 degree and you want to keep the indoor temperature as maybe 20 degrees. So, there is a difference, that 38 minus 20 or whatever it is. So, suppose I have another example. So, I have a wall area of 40 meter square and a window area of 10 meter square. Their outdoor and indoor temperature difference is 18 degree centigrade. I am keeping 18 degree lower inside and outdoor temperature is higher, and the U values are 1.5 and 3. Then I can calculate with the straightforward manner that what are the amount of Q, that is how much watt is the heat gain through this conduction. So, I have multiplied 1.5 is the U value of the wall and 40 is the area, 18 is the temperature difference. This is for the window, window area is 10 and this 3 is the U value of the window, and this is your, again the temperature difference is same because outside inside. So, I can add, and then this is the, I can have the another kind of solution where I can find out the average U value. So, multiplying the U value of the wall and the area of the wall plus the U value of the window and the area of the window, and divide that by the total amount of the area, that is 50 meters square, and I get a particular average U value of the wall as 1.8 watt per meter square per degree C, and then I just multiply this 1.8 is average U value. The total area is now 50, the 10 plus 40, and this is your 18 is the temperature difference, same value I will get for that. So, specific heat is another thing that will actually come into the place, where we can define the specific heat as to the heat that is required to raise 1 degree temperature of 1 kg of that particular object or any matter or any material. So, that means to increase the temperature by 1 degree, how much heat it store or it required. So, the specific heat is very high. So, you need more the heat to actually put in and raise the temperature by 1 degree. So, the high specific heat material will definitely give you better heat storage capacities also. So, from that point of view, we can come to a particular concept of the thermal mass, where this thermal mass is nothing but the product of this mass multiplied by the specific heat. So, the heat energy, that how much joule is required to increase a temperature delta T, suppose delta T, let us suppose 1 degree and you have 1 kg of thing. So, multiplied by the specific heat. So, that much amount of heat will be required. So, just increase the temperature, and if you do not increase the temperature, temperature will not be conducted from one point to the other, because there should be a differential temperature exist in the layers of the thick brick wall also, and then it will be transmitted from one point to the other. So, that is why this thermal mass is very important to see that heavy thermal mass will store more, the less thermal mass, lightweight and all these things will store a little less. So, here when we see another kind of the property called the thermal diffusivity, we see if these three things comes together, the thermal conductivity, the K value is a very the fundamental property of a material, density another fundamental property, density gives you how much the weight and all these things, same volume high density will give you more weight, and the specific heat. So, if the thermal conductivity is high, the rate will be faster, rate will transmit from one point to other, one layer to other. If the density is high, it will be slower because the material has more weight. So, it can store more energy, more heat, and the specific heat if it is high, again it will be slower because specific heat high means to raise 1 degree temperature required lot of joule of energy or lot of joule of temperature. So, from that point of view, if you see if you have a kind of another the equation or maybe another kind of the property we can devise, that K divided by this d by C, it should be d, not d, it should be rho. I will change it rho. So, then this is called the thermal diffusivity. See the K by rho into C, that means if it is increasing K value, it is thermal diffusivity is increasing, where if the rho and C drops, it will be going to increase the thermal diffusivity. So, high thermal diffusivity means it will be very fast, the heat will transmit from one layer to the other, it goes very fast. So, that what I have discussed, the high thermal conductivity, high thermal that will be the high diffusivity, density multiplied by specific heat, that product also in the thermal mass what we have discussed, and that also goes with the high amount of diffusion or whatever. So, these are the some of the building materials, the K value, density value and the specific heat value is mentioned, and I have calculated the thermal diffusivity. You see the highest comes over here, the concrete is very high diffusivity, then that means it will be very fast rate, it will actually the temperature or the heat will be absorbed in the layers and layers and layers, and then it will be go. If you see the lowest one, again it is the EPS, that is the extended polystyrene, it will be very slow, it will actually the heat up one layer and then it will go to the next layer, almost 6.6 times, no 660 times, maybe not 6 times. So, now you see the periodic heat flow, there are fluctuations of the heat in 24 hours temperature. So, it will store heat in one point and then it will release it to the next the inside. So, there is a the heat the temperature difference in the outside and the temperature difference in the inside, which can be shown like this. That the black color, the curve, it is a kind of a periodic curve. This periodic curve is definitely having kind of changes in the different seasons, but in a particular season this it will be a periodic in nature, and this red color one is the indoor temperature curve. So, there is a peak difference and there is a shift of the peak also. So, maybe at the particular maybe around 12 or not 12, it is maybe up to PM, the peak is there in the outdoor temperature, but my peak in the indoor temperature is almost about maybe 9 PM or so. So, like that. So, there is a difference in this. So, this difference has been countered by, or there is a two parameters are taken out. One is the time lag or the phase shift, the how much is the difference, how much from 2 PM to 9 PM or how much 7 hours or whatever, and another one is the decrement factor, that is the what is the amplitude attenuation, that is how much is the TI maximum and the TO maximum, these two are taken care of. So, impact of the thermal mass, if I have a very high low thermal mass, so that peak attenuation of the amplitude will be not be so. So, it will have a very less amount of time lag also, because within 1 hour it will be or less hours it will be actually the time lag or the peak will be there, and this very high decrement factor. Whereas, if it is a kind of a high thermal mass material, then it will be reverse way, it will be very flat and it will be a more time lag and the low decrement value. So, I have the relation between the time lag and the wall thicknesses. If the wall thicknesses increases, the time lag increases, okay, and because of the different type of densities, time lag also increases. And in another way, it is if the wall thicknesses increases, the discriminant factor decreases, and because of the insulation outside, insulation inside, and in uninsulated case, it will be also going to be a changes. So, it is always better to have the outside insulation. If you see, the outside insulation gives you a better kind of the discriminant factor kind of the scenario. So, that is all for today's lecture, and these are the references. So, what we have done over here, we discussed about the k values, we discussed about the u values, and which is a very major factor, plays the role in the time of your heat gain or heat calculations of a building. Also, we discussed the temperature variations outside and inside, and the phase lag and the amplitude attenuation. Thank you very much.